Hi everyone, my name is Justin Cross and this is my Transport1 homework 4 solution. So in problem statement we are given that there are two cylindrical tanks connected with piping at the bottom. They both have a certain amount of fluid in each and the specifications of all of that are given here. So the radius of the first tank we're going to say is 4 meters while the radius of the second tank is 2 meters. We're also going to say the height of the fluid in the first tank is 5 meters, and the height of the fluid in the second tank is 3 meters. So they're both above the radius. We're also given the area of the piping that connects both tanks 1 and 2, and the piping that leads out of tank 2. The area of both of those are 0.2 meters squared. We're also told that into each tank there is an inlet flow. We're going to call that Q in 1 and Q in 2. And we're told that at t equals 100 seconds, the inlet flow into tank 1 becomes 80% of what it normally was. And the same thing for t equals 200 seconds, we're told that the inlet flow into tank 2 becomes 250% of what it originally was. And what we want to do for part 1 of this problem is to derive equations for both Q12, the flow between 1 and 2, as well as the flow that leads out of 2. So let's start with Q12. We know originally by definition, a flow rate Q equals an area times a velocity, just like that. So if we want to find Q12, we're going to need the area of the pipe between 1 and 2, as well as the velocity of the fluid going between them. Well, we're given A12 right here, 0.2 meters squared. So to find Q12, all we need is V12. Now to find V12, we've done this before. We want to use the Bernoulli equation to solve for the velocity. So if I write down the Bernoulli equation here, so P2 minus P1 over rho, the density, plus the gravitational constant times Z2 minus Z1, the change in height, plus V2 squared minus V1 squared over 2 equals, we're going to ignore the frictional heating in this equation, so that equals 0, just like that. Now, if we want to define where points 1 and 2 are, we're going to say point 1 is, we'll say here, 1, and point 2 is right here, right at the inlet of that flow. Now, what do we know because of that? Well, if we say they're on the same level, we're going to have a lot of cancellations here when we get out my red marker. If they're at the same level, there's no change in height, so Z2 minus Z1 becomes 0. So all of this goes away. We also say that the inlet flow right here, we're going to say is equal to the atmospheric pressure. So I'm going to call that 0. So the pressure at 2 becomes 0, as well as we're going to say the velocity at point 1 equals 0. So V1 squared equals 0, just like that. Now we can solve for P1. We know what P1 is, so we'll say negative rho GH. That's what the pressure is, rho GH over rho plus V2 squared over 2 equals 0. And from here, it's just a matter of basic algebra, and we're left with solving for the velocity, for V2 equals the square root of 2GH, just like that. Now we can use this equation that we just found for the velocity, and we can plug it into our flow rate equation. So if we do that, if we look at Q12, the flow rate in between tanks 1 and 2, we're going to say that equals the area between 1 and 2, which was given, times the square root of 2g, and then for h, we're going to use the difference in between the tanks. The difference in between the heights of water, or whatever fluid, in the tanks. And because it's underneath a square root, we always want it to be positive. So we're going to use the absolute value. So absolute value of H1 minus H2. Just like that. Now, what happens if the height 1 goes underneath where height 2 is. So now height 2 would be bigger than height 1. We need to take into account the sign change for when that happens. So we multiply this by sine, not the trigonometry sign, but SIGN of H1 minus H2, just like that. And when that happens, it will take into account that one is now higher than the other. So this right here is actually the equation we wanted for the flow rate between 1 and 2. Now, if we apply the same methodology that we did for Q2, so the flow rate going out of tank 2 equals the area times the velocity. And just like before, we'll say Q2 equals the area times the square root of 2GH2. And because we're not taking a difference in between two different tanks, we don't have to worry about the absolute value. And same with the sign change, we're not taking into account a change in height in between two tanks. So this is our equation for the flow rate going out of 2. Now what we're going to do next is we're going to perform a mass balance, and we're going to take into account Q2 as well as Q1 and 2 to find the change in volume of the tank. And eventually what we're going to do is we're going to find the change in height of the tank, with respect to time. So what I'm going to do to get a little more room on the board, I'm going to make a cut. I'm going to move both these equations up to the top, and we will continue with this mass balance. All right, with our two flow rate equations here at the top and more room on our board, we can move on to our mass balance. So I'm actually going to use our blue marker from here on out because my black marker died. I'll go get a new one, don't worry. So if we look at our first tank here, we look at the volume and change of time. So dV of 1, dV1 over dt. So our change in volume over change in time is going to equal everything coming into tank 1 minus everything leaving tank 1. So that equals our inlet flow into 1, so Q in 1, and then what's coming out minus Q1, 2. Now because Q1, 2, and Q2 are pretty big mouthfuls or handfuls, I'm just going to write Q1, 2. Just know that we already know what that equals. So we do the same thing for the second tank. So we say dV2, change in volume of the second tank over time, equals, and then we follow the same idea. So we have a Q in 2, and then what's also coming in is Q1, 2 plus Q1, 2 minus Q2, just like that. Now, what do we know about the change in volume over time? So our dV dt, it equals the cross-sectional area around, so AC, times the change in height over time, dH dt. And dH dt is actually what we're looking for. We want to find the change in height as it changes with time. So how do we manipulate these two equations into giving us dH dt? It's pretty easy. We just substitute this dV dt, the change in volume, with this product right here. So this becomes AC1 times dH1 dt equals Q in 1 minus Q1, 2, just like that. And then we divide across by the cross-sectional area, and we get dH1 dt equals Q in 1 minus Q1, 2 over the cross-sectional area at 1, AC1. And we follow the same steps for dV2. I'm not going to show them, just like that. So we get dH2 over dt equals Q in 2, Q in 2 plus Q1, 2 minus Q2, all over the cross-sectional area at 2. So AC2. Now, if you think about this, the cross-sectional area is actually changing as the height changes, right? So how do we find that? So we want to find that in terms of the radius and the height at the water. So how do we do that? We can do that with a little bit of geometry. So let me draw our tank here at a certain height. We have our water level, we'll call that H. We also have our radius, just like that, R, and we'll draw the final part of our triangle, just like that. So big R is the radius of the tank, while small r is the radius that we want to solve for. So we can use Pythagorean's theorem if we redraw this triangle here, just like that. So this is big R, this is little r, and then if we look here, this right here is r as well, and this big part is h. So if we do big H minus r, that leaves us with that final part of the triangle. So h minus big R, just like that. And because this is a right triangle, we can use Pythagorean's theorem to solve. So this becomes big R squared, the radius of the tank squared, equals little r squared plus h minus big R squared, just like that. And then with a little bit of algebra, we can solve for this little r. So we get little r squared equals big R squared minus h minus big R squared, just like that. Now, we didn't want the radius, we wanted the cross-sectional area, right? But we know the area of a circle equals pi r squared. So that means the cross-sectional area here, so AC equals pi times this r squared, which we just solved for. So big R squared minus h minus big R squared, just like that. And we plug this cross-sectional area into these two equations here, and that'll actually give us our final equations. So we'll just erase here, AC1 and AC2. This becomes pi R1 squared minus H1 minus R1 squared, just like that. And the same idea over here, we go pi times R2 squared minus H2 minus big R2 squared, just like that. And these are actually the two equations we're going to take to the next part of this problem. The next part of the problem being, we will use these two equations within Google Colaboratory. We're going to use Python to solve and graph the heights and the flow rates of this of these two tanks with respect to time. So I'm going to go and get onto Google Colaboratory, and I will see you there. All right, welcome to Google Colaboratory. So this is an extension made by Google to run Python, which we're going to use to help solve this question. So the first thing we're going to start with are our imports. I've got them over here. Let me copy and paste that over. So some of these imports, the scipy.integrate, we're going to use solve IVP to actually solve our equations that we got in part 2. Jax and jax.numpy are two different imports made by Google to help with calculating derivatives a little easier. We're going to use the make subplots from Plotly to make our subplots. And then we're going to use plotly.graphObjects to help graph our objects in our plots. So shift enter to run everything. There it goes. All right. So now we can start with the initial conditions we were given, like the radius, the cross-sectional areas, and the initial heights. So we'll start with the radii. So we have R1, we have an R2, we have an H1 initial. Make that lowercase, H1 initial, H2 initial, area, cross-sectional area of the pipe from 1 to 2, and area of 2. And what do these equal? A1 was 4.0, oops. This was 2, just like that. Initial height for 1 was 5, I believe. So 5.0. This was 3 meters, 3.0, and both of these were 0.2. 0.2 and equals 0.2. Let's see, what else? We're going to use the square root of 2 times 9.81, or the gravitational constant, a lot while calculating these things. So we'll do that separately here. So SQ2G, oops, SQ2G equals square root of 2 times 9.81. Just like that. What else? Well, we're going to run this from a time 0 to a time t final, right? So we need an end time for our graph. So we'll do t end. We'll say that's like 2,000 seconds. Okay? Now, what else? We had the flow rates, the initial flow rates from 1 to 2 and going out of 2. So we had Q12, the initial there, and Q2, the initial, just like that. And these are actually going to come straight from the equations that we had from parts 1 and 2. So this was A12 times SQ2G times the square root of the absolute value. So value of H1 initial minus H2 initial. Oops. H2 initial, just like that, times the sine of H1 initial minus H2 initial, just like that. And that was from the original parts of this equation. And the same thing goes for here, which is A2 times SQ2G times the square root of H2 initial, just like that. And then finally we had some volume balance. So we had Q1 initial, well, Q1 in initial. So that was the flow rate of the inlet of the first tank. And we said that equals Q2 initial at a steady state. So everything that goes in must equal everything that comes out. And then Q2 in initial, the same idea, everything that goes in equals everything that comes out. So that's Q2 initial minus Q12 initial, just like that. So that is our imports. What's next? We want to define dH dt. So define dH dt, and we give it time t and our height h, just like that. So we're going to have two equations. So we're going to have 2 times and 2 heights. So if we say h1, we're going to say that's the first element in our array of h. And same thing with h2. It's going to equal the second element in our array of h. So h1, just like that. And we're going to return here. We're going to return 2 equations. Let's see. It was our Q1 in, sorry about that, Q1 in minus Q12, Q12 divided by AC, right? And then that was for the first tank, and for the second tank we had Q2 in plus Q12 minus Q2 divided by the cross-sectional area. And again, all of this came from parts 1 and 2, where we derived all of these equations. We also derived the cross-sectional area, so I'm actually going to add this up to the imports here. So if we defined AC in terms of the height and the given radius, just like that, what did we say the cross-sectional area was? So we're going to return pi, jmp.pi times the big R squared minus h minus the big R squared, just like that. All right, what is next? What's next? We wanted to find, so we never took into account the time change or the flow rate change at t equals 100 and t equals 200. So that's what we need to do here in Python. And to simulate that, we're going to use something called a sigmoid function.
I'm not going to get into the details of what a sigmoid function is. Oh, okay. But what we need to know is that a sigmoid function will take a function from a range of negative infinity to infinity and squash it down to a range of -1 to 1. And we're going to use that to simulate the switch in flow rates at t equals 100 and t equals 200, respectively, for flow rate in 1 and 2. So if we define switch, we're going to call it switch, where we're going to give it a t, a v1, a v2, the time at which it switches, so t switch, and its scale, just like that. And the way we do this, we're going to return, we're going to use a sigmoid function, so jax.neuralnetwork.sigmoid, just like that. All right, now we give it the t minus the t switch, so t minus t switch, like that, divided by the scale, yeah, and then multiplied by v2 minus v1 close plus v1, just like that. And what this will do is it will take into account the time at which a flow rate switches, and we're going to use it to model the flow rate respectively. So if we go in and now we want to model the flow rates, so Q1 in and Q2 in, so we define Q1 in, and what is it going to need? It's going to need a time, right? Because it's going to switch at a certain time. Oops. There we go. And we're going to return here the switch. So the switch at, maybe shift enter here, because that should have updated. Switch, there we go. So at the time t, the v1 is going to be q1, what do we call it? Yeah, q1 in initial, and v2, it was 80% at 100 seconds. So 0.8 times q1 in initial. The time t switch is 100, and scale we're going to say 0.01, just like that. And we're going to do the same thing for Q2 in. So if we copy and paste this down here, so if we call this Q2 in initial, so T Q2 in initial, instead of 80%, it was 250%. So 2.5 times Q2 in initial, and at 200 seconds instead of 100 seconds, just like that. All right, so now if we go back to our dHdt, instead of using some of these initial ideas, we're going to use some of the updated ones, so like our Q1 in and our Q2 in. So we say our Q12 and our Q2. We're going to solve for those here now. Oh boy. And Q2. Well, what do these equal? Well, we've got them both up here, right? So if we take this and copy and paste down here, oops, there we go. Control V, tap this over. Come on. Come on. There we go. Instead of initial, we're going to take out all the initials. So instead of H1 initial, H2 initial, it's just H1 and H2. Same with here. Same with here. And there we go. Now this AC, we had it in terms of H initial, well, H1 and R1, just like that, and H2 and R2, just like that. Oh, it's a minus, not an equal. Perfect. And so here, I believe we're now actually ready to solve these. So our result is going to equal solve IVP. Let's see. We need a function. We're going to call that dHdt, which we already solved for. What's next? Our t span. We go from 0 to t end. Our initials, so H1 initial and H2 initial, just like that. our method for solving is going to equal radu, and dense output is going to equal true, just like that. So let's see if this runs. Oh, 0 instead of O. Let's see. HDT. Q12 divided by AC12, Q1 R1. You know what? I found it. Found our option. So these are a function of time, just like that. So we need to give it the given time. There we go. And that should run now. Let's see. It's running. It's really running. All right, there we go. So now we want to be able to solve, we want to graph this result. So if we take we want x values for our x-axis, so we're going to call that tplot equals jmp.linspace, and it's going to go from 0 to tn. It will say 501 points, okay? Now our solution is going to equal our result.solve for tplot, just like that. All right, and now I believe we are ready to graph these. So to start these graphings, we're going to make a figure. So figure equals make subplots. How many rows? We're going to want 1 row. Row equals 1. Oh, get out of the way. Row equals 1. Rows, columns equals 2. Get rid of that. There we go. And we're going to call this fig, not feg. There we go. So we want to add to this. So figure dot add trace. Where's the trace? We want a graph objects dot scatter. There we go. Where our x is going to equal our tplot. Our y is going to equal our solution, the first element. We can name it. Equals, we'll call it h1. There we go. And this is going to go in the first row and the first column. So row equals 1, column equals 1. And let's see if we can see that. Oh, misspelled it again. Figure. There we go. Yeah, so there it is. So now if we do the same thing for h2. So if we copy and paste this down, let's see, xtplot solution at 1. And we call it h2. There we go. So now we can see both of them. There we go. Perfect. And now say we want to add the flow rates. That's pretty easy too. So figure add trace, what another scatter plot. Tplot, what is this y going to be? It's going to be the flow rate from 1 to 2 in, oh, my bad. The flow rate from 1 in at times tplot, just like that. And we'll call that Q1 in. It is actually going to go in the second column, just like that. Now if we copy and paste that down, we can call this Q2 in, and again in the second column. So we paste, and there we go. We can actually see that the flow rate changing from what it was originally to 80% of what it was originally, and then increasing the second one up to 250%. That's on the right-hand side here. On the left-hand side, we can actually see the height change as it goes. So that is exactly what we wanted to do. We found plots for H1 and H2 as the Q1 in and Q2 in change at 100 and 200 seconds.